Alright, we're getting into, instead of arithmetic sequences, geometric sequences. I'm just going to do this explore here. Just as a kind of a preempt to what we're doing here, we are now talking about, instead of an addition rule, a multiplication rule. And if you look at this, this is the stages of what's called a fractal tree. Stage 0 says one line is drawn. Stage 1, you can see that there's two additional lines right here, right? One here and one here. Stage 2, if you count the small branches, 1, 2, 3, 4. Stage 3, 1, 2, 3, 4, 5, 6, 7, 8. So what we're doing is we're going to end up counting the branch. It says complete the table to discover the pattern for the number of new branches. We're looking for new branches. And as we can see, 1 just has one. Stage 2, right? Or stage 1, sorry, has 2. 1, 2. And we can see the pattern here is we're really just multiplying by 2. Alright, so this will go 1, 2, 4, 8, and times 2 is 16, 32, and 64, right? And this would be 2 times 4, which would mean, hey, I've got 1, 2, 3, 4 branches, and I double both those to get my 8. So this would be 2 times 8, 2 times 16, and 2 times 32. So we're basically taking the previous one and doubling it. Taking the previous number and doubling it. What we end up with the power, right? This is actually 2 to the 3rd, 2 to the 4th, right? 8 is 2 cubed, plus another 2 is 2 to the 4th, 2 to the 5th, 16 is 2 to the 4th, plus another 2 is 2 to the 5th, and this would be 2 to the 6th. All right, so let's go ahead and write a function based on that. All right, n to the s stage, right, assuming that this is the 0 stage, right, is going to be equal to 2 to the stage power, right? 2 to the 0 is 1, right? 2 squared is 2. 2 to the 3rd is 8. 2 to the 6th is 64. So whatever I plug into that stage gives me my final number of new branches, all right? My domain, right? My domain for S. Let's talk about the domain of S. All right. My domain of S would be, you know what? All real integers, right there. So anything over 0. Sorry, integers over 0. And this represents the number of stages, all right? Or we could say the number of times the tree branched. Just so you know and understand that, right? It branched once here, there, and there. Branched twice here. There's a branch there and a branch there. So how many new sets of growth come off? And those new sets always come in 2s, don't they? So we're going to write the range. So we'll say what that range means. This is equal to the number, that's our output, of new branches, right? For each stage, right? There's a number of new branches. This will be our output or our range, right? So if I was going to do this, we can show a pattern, right? We could say, hey, it started with 1, it doubled, it doubled, it doubled, it doubled. And once you show a pattern, you can say dot, dot, dot. Well, there's another way you could do it, right? You could say, or the number of, and you could give an equation that represents it, which we had 2 to the s power, and that is going to represent our range where s is a, let's say s is a whole number, right? Because we know we're talking about stages as whole numbers. Alright, so there's another way you can represent a range. You can put an equation in there and define what it is, make sure. Alright. Now we're going to come down here, we're going to graph the first 5 values. So let's go ahead and do that. All right. 1 was 0, or 0 was 1, 1 was 2, 2 was 4, all right. 3 went up to 8, 4 went up to 16. I think I'm running out. I don't think 32 will fit on here, but 32 would be the next one. And we can see that this is increasing. All right. So there we go. We have done n of s. So our first example geometric routine in which the multiplication rule means we're, instead of adding as we would in an arithmetic sequence, or multiplying like a geometric sequence. Number 2. All right, let's fill out this data, and we'll see if we can get through this page too. We can do 2 pages at once, right? It says this. It says, now fill out the table representing the branch length. And I just want to show you what they mean here, right? Although there's more branches each time, let's go ahead and look back at what we just did, right? So I'm pulling it back up. Although there's more branches each time, we're going to say those branch lengths reduced by 1/2. This is definitely not a good representation of that, right? Because that's probably not 1/2 of this, but their goal is to say, hey, you know what? Let's go ahead and see how long the branches are, and we're going to say each branch gets subsequently shorter by about 50%, right? And so we can say at the first stage there was one branch which was as long as itself. Second stage, or stage 1, if you're counting number of stages, there's 2 branches, but each one was half the length of the original branch. And as subsequently they go to 1/4, 1/8, 1/16, 1/32, or if written as an equation, we could say 1/2 to the nth, right? So the number tells us how long those branches are. All right. So let's write an equation. Well, you know what? L to the S, instead of increasing, we're decreasing, right? We're actually dividing by 2 our size, right? Instead of multiplying by 2. So instead of 2 to the S, we're going to 1/2 to the S. Our domain hasn't changed much, right? Our domain for S is still whole numbers, right? Whole numbers. And I'll say S is what? Greater than or equal to, starts with 0, right? But whole numbers does it, right? I actually don't need to write that. Whole numbers, there's no negatives, no fractions, so really I could just write whole numbers. In my range, we can do 2 things again. We could say, hey, you know what? Let's go ahead and talk about our range as, what's our range? L, our length, as a kind of a pattern, 1 to 1/2 to 1/4, dot, dot, dot. Or once again, we could write our range as a formula. We got 1/2 to the S power. And we'll say again, where S is a whole number. I'm running out of room over here. Those are 2 ways to write them. Okay? If we graph these, all right? So, wow. So at 0 we were 1 long, right? At 1 we were half that, 1/2. At 2 we were 1/4. At 3 we were 1/8, 1/16. We could go to 1/32. And discrete numbers, we're not attaching these anymore. And obviously this one's decreasing. So we're done with these first 2 pages as soon as we finish this out. It says I can write an explicit or recursive rules for geometric sequence, and a sequence in which a common ratio, that means we have a multiplication rule, between the terms is this. My ratio is any term divided by the previous term. And I'm going to show you how we can get the ratio up here just so you know. My ratio, which we saw was 1/2, right? I could take any term. So let's take term 5. We'll say, right, f of 5 divided by f of 4 is equal to 32/16, which is 2. I'm sorry, I did that backwards. F of 5 divided by f of 4 equals, instead of 32, that's 1/32 divided by 1/16, which gives us 1/2. I used the wrong column here. And you can see how that's how we get a ratio, right? The first ratio was 32 divided by 16, 2. The second ratio for this equation, the L of S equation, the length of the is 1/2. And there it is. First 2 pages.